Welcome to AI Frontiers, where we explore cutting-edge developments shaping artificial intelligence research. Today, we're diving into revolutionary advances in machine learning from December 2025. From transformer compression breakthroughs to physics-informed networks, we'll uncover how researchers are challenging conventional AI wisdom. With 128 research papers synthesized into key insights, this episode reveals how efficiency, interpretability, and principled approaches are reshaping the future of artificial intelligence technology. Picture this surprising truth about AI efficiency. What if smaller models could reason better than giants? Recent research has shattered our assumptions about artificial intelligence capabilities. A tiny model with just 76,000 parameters has outperformed massive language models on reasoning tasks. Even more shocking, researchers discovered that most transformer attention connections are actually redundant noise. Over 99% of attention patterns can be removed without performance loss. These revolutionary findings suggest that intelligence might fundamentally be about compression, rather than memorization, challenging everything we thought we knew about building effective AI systems. To understand today's machine learning landscape, imagine the field as a vast metropolis under constant construction. Machine learning forms the downtown core of this AI city, where fundamental algorithms and mathematical frameworks power every artificial intelligence application you encounter daily. This isn't just about building bigger computational skyscrapers. It's about discovering the architectural principles and infrastructure, innovations that make the entire ecosystem of AI function more efficiently and reliably. Every voice assistant query, every automatic photo focus, every medical AI diagnosis represents practical applications of the fundamental research we're exploring today. Machine learning operates like a diverse, evolving rainforest ecosystem. Just as a rainforest contains everything from towering trees to microscopic organisms, each playing crucial roles in overall system health, machine learning encompasses specialized algorithms, evolved to tackle different learning challenges. Different species of computational approaches have adapted to specific niches, from optimization methods that train neural networks to theoretical frameworks that help us understand when and why learning succeeds or fails. Each technique has been optimized for different aspects of the learning problem, and the ecosystem's health depends on this diversity and interconnection between different approaches. The first major research theme focuses on efficiency and compression in large language models. Think of packing for a month-long trip with only carry-on luggage. You need strategic compression without losing functionality. Lessons and colleagues revolutionized transformer attention compression with their KQ-SVD method. They discovered that previous compression approaches were fundamentally suboptimal because they tried to compress individual components feeding into attention calculations. Instead, KQ-SVD compresses the attention relationships directly through matrix decomposition. This breakthrough achieves dramatic memory reduction without performance loss, potentially making advanced AI systems accessible to researchers and organizations with limited computational resources. It represents a complete rethinking of redundancy in neural attention mechanisms. The second theme explores interpretability and mechanistic understanding of neural networks. Imagine being a detective studying how a master chef creates incredible dishes. You could taste the final result, but that doesn't reveal the technique, timing, or ingredient interactions that make it work. Similarly, Dre and colleagues developed sparse attention post-training methods to peer inside transformer models and understand not just what they do, but how they accomplish their tasks. Their research reveals enormous redundancy in transformer attention patterns. Over 99% of attention connections can be removed while preserving performance and actually improving interpretability. This discovery challenges fundamental assumptions about how these models work and opens new pathways for understanding artificial intelligence mechanisms. The third theme involves integrating physics and domain knowledge into neural networks. Consider teaching someone to ride a bicycle by showing thousands of pictures versus explaining the physics of balance, momentum, and steering. The second approach incorporates fundamental principles that make learning more efficient and reliable. Golder and colleagues exemplify this philosophy with their DAE hardnet architecture. Instead of hoping neural networks will discover physical laws from data alone, Physics-informed networks explicitly encode constraints like conservation of energy or mass into the architecture. This represents a significant shift from pure data-driven approaches toward hybrid systems that combine neural networks' pattern recognition power with the reliability of established scientific knowledge. Let me share the most striking discoveries reshaping our understanding of machine learning. First, the KQ-SVD work proves that virtually all previous transformer compression approaches were fundamentally suboptimal. Second, researchers achieved provably robust neural networks with mathematical guarantees against adversarial attacks, showing significant accuracy improvements over existing methods. Third, new theoretical frameworks reveal that recurrent networks' ability to learn long-term dependencies depends on complex interactions between gating mechanisms and noise characteristics, not just numerical stability as previously thought. Fourth, fundamental scaling laws for dataset distillation show that size requirements scale linearly with configuration diversity. Finally, transformer attention can be made orders of magnitude sparser, while actually improving interpretability, challenging conventional wisdom about dense attention necessity. Today's featured research comes from Isaac Liao and colleagues, whose CompressARC work fundamentally challenges how we think about artificial intelligence and reasoning. Their tiny model with just 76,000 parameters tackles abstract reasoning puzzles that typically require massive computational resources. The revolutionary approach uses no external training data, learning during inference only. Based on the minimum description length principle, CompressARC achieved 20% success on the ARC AGI benchmark. This proves that reasoning capabilities don't necessarily require massive computational resources, suggesting that elegant mathematical principles can compete with brute force scaling approaches in artificial intelligence development. CompressARC treats intelligence as a compression problem, where each puzzle becomes a compression optimization challenge. The core insight is that the shortest description of observed patterns enables the best predictions for missing pieces. When you understand something deeply, you can describe it simply and elegantly. When confused or uncertain, explanations become verbose and convoluted. This approach aligns with cognitive science theories, suggesting that human intelligence is largely about pattern recognition and finding elegant, generalizable explanations for observations. The success of CompressARC implies that reasoning might not require vast amounts of memorized information, but rather the ability to identify and exploit structural patterns in problems. The implications of CompressARC extend far beyond academic curiosity. This compression-based approach opens entirely new research directions accessible to researchers with limited computational resources. It naturally provides interpretable explanations for solutions in terms of discovered patterns and structures, making it more transparent than black box neural networks. The work suggests new approaches to few-shot learning, where systems quickly adapt to new problems with minimal examples. Perhaps most importantly, Liao and colleagues demonstrated intellectual courage to question fundamental assumptions that the entire field had largely accepted. Their work reminds us that mathematical insight and principled thinking can lead to breakthrough discoveries, even in an era where AI success often seems to require massive computational resources. Looking toward the future, we're in the early days of aviation for machine learning, discovering fundamental principles that will enable everything from practical deployment to theoretical breakthroughs. The convergence of efficiency and interpretability appears particularly promising, as sparse attention work demonstrates. These goals can be complementary rather than competing. Domain knowledge integration with machine learning represents another frontier, with enormous potential for revolutionizing fields like climate modeling, drug discovery, and materials science. Theoretical foundations being established today will likely enable more systematic approaches to AI system design, moving beyond trial and error toward predictable, reliable engineering. The democratization of AI capabilities through efficient methods could reshape who can participate in research and development. Today's journey reveals a field in remarkable transition. Researchers are moving beyond simple scaling paradigms toward more elegant, principled approaches that achieve better performance with fewer resources. Fundamental assumptions about what makes AI systems effective are being reconsidered and challenged. We're glimpsing the potential for AI systems that are not only more capable, but also more interpretable, efficient, and reliable. The work of researchers like Liao, Lessons, and Dre reminds us that the most important advances in science often come from questioning conventional wisdom and thinking deeply about fundamental principles. As machine learning continues evolving, these insights will likely prove to be stepping stones toward more sophisticated and beneficial artificial intelligence systems. This presentation was created through advanced AI synthesis and review processes. The synthesis utilized GPT Anthropic Claude Sonnet 4 from May 2025, with text-to-speech powered by DeepGram technology and image generation using OpenAI systems. All content underwent expert human review for accuracy, though some oversights may exist, and references are provided for verification. This collaborative approach between artificial intelligence tools and human expertise demonstrates how modern research synthesis can make complex technical content more accessible while maintaining scientific rigor and accuracy. Thank you for joining us on AI Frontiers today. I encourage you to explore these papers yourself and consider how these advances might apply to your work or interests. The field of machine learning is more accessible than ever, and important discoveries may come from unexpected directions. Share your thoughts about today's breakthroughs on social media, and let us know which findings you found most intriguing. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv preprint server.